I hope I'm audible. Yeah. Hello all. So, welcome to image processing session where you will learn how to see like a robot and understand the process of how human visualization works and how we can actually map it to a robot. Huh? So I hope all of you must have worked with some or the other projects in image processing or perception or some kind of object detection or some kind of color detection, something. How many of you have worked on it? Any, can I see any hands or responses? Yeah, sorry for the delay. So let's start. Yeah. So basically, the way we look at the world is beautiful. It's actually it's actually the image that comes into our eyes. The light that gets onto the object and it gets reflected from the object and comes to our eyes, and inside our eyes it gets an image and our brain processes all that, right? It's a beautiful process. So vision is the most advanced of our senses, so it's not that surprising that image play a single most important role in perception. Yeah. So we'll be understanding the whole journey of how this is played throughout the robot, how a robot understands the image, an object, and how it processes it. Yeah, yeah. I hope I've shared the screen. I hope it's visible to everyone. Cool. Yeah. So throughout the journey, you'll be going through all these stages. Is what is an image, logic of colors, the paradox of blur, the geometry of sight from shapes to names and digital street signs. Huh? So, what is an image? It's a basic thing. So, uh, an image will look like we all have seen pixels and all those columns and all these diodes and all we understood in our basic electronics classes, right? EDC. Yeah. So basically, these images are columns of blocks, you can imagine, which exactly, yeah, so two-dimensional signals, yeah. So a human, how human perceives an image is like a signal, okay? It's like a spectrum of colors. So you can see the the electromagnetic spectrum lies from one end to another, but a human can only perceive such a small um, band of signals, right? What about the rest? Using this small band of colors, we are we yet to we still understand how things are, what things are, what color things are, how beautiful the nature is, what color the water is. All that things we understand using our eyes. Our brain processes it. It's all, it's all intuitively and naturally coming out to us, right? So, what do you think? How a robot does this processing? So basically, all these machines are capable of understanding the other spectrum of light, like UV, X-rays, gamma, infrared, microwave, and radio. They can actually go through all these spectrums and pers- make a perception out of it. Basically, they can get the information that they need to get out of these spectrum, huh? But a human can only understand the small band. So how did they do all these? Let's understand. Yeah. So a machine, basically, you must have seen how a camera works. It goes through a scene, and then the scene focuses a light. Just a second. Yeah. So an image, basically, from the light, that the light gets reflected to from an image. Sorry. So basically, the light gets reflected from the object and goes through a lens and gets inside the array. So if you look inside the camera, there's a array sensor inside it. So what happens is this object gets divided. It's a signal, right? How do we extract information out of that signal? So this analog signal that is captured inside this array of sensors basically gets sampled by all these small sensors that is attached to the column of sensor. What happens is uh, an analog signal is sampled by all these pixel arrays, and then they are converted into pixels, basically. Yeah. So these sensor arrays converts the light into pixels, and then they are processed it, and then they are quantized and brought it into this big image that we see in our all days. We see in our screens or anything, we present it towards anything. Yeah. So this is the image that we come out with at the end of the result. So it's how beautiful it is done, right? Yeah. So let's go further and understand how exactly this spreadsheet of columns and rows looks like. So you can see here there are random numbers. So I'm taking an example of a black and white image. You can see. So consider this as a small section of the whole image that we got. Uh, You can see certain numbers: 737, 60. It goes on in and around some 200 and something, right? So any guesses? Why is this 207 and all are there? Any guesses? Anyone knows? Yeah, cool. So the value is from 0 to 255. How do they get this 0 to 255? Okay, I'll tell you. So what happens is this is an 8-bit image. Yeah, ADC. Yeah, exactly what I mentioned earlier. So an analog signal comes through those lenses and then goes through that sensor, and then they're sampled and quantized. It's all same process as ADC, right? How an analog to digital signal is converted. So what you are seeing here is a digital signal of an analog image that has been converted and kept in front of you. So when you zoom into that image, you will see all these blocks. So each blocks, so we are considering a black and white image. So consider 0 as the uh, darkest the darkest pixel, and 255 as the most whitest pixel. Okay, so you can see. So if it is 7, that is black, and when you go towards the highest number in the whole column, you can see it's 210 is the highest column, or is it anything else there? No. So it's 210. So 210 is the brightest column, right? So that's how an image is formed. That's how the background story of images. Robot, a perception of a robot actually looks into this certain columns of spreadsheet. So every technique that we cover today is just a math on this grid. So no formulas that we will be exploring. So no need to worry about it. We are not going deep mathematics. It will be pure demonstration and how these things you can take as an application and understand from different kind of maybe debugging something. So you might face certain something, some problem here and there, right? Yeah. So let's go to, I'll show you a more detailed example. So how a RGB image looks like. Yeah. Yeah. As you can see, this is basically an image. It's highly, you know, compressed. It's only basically it's shown here so that you can actually zoom into it and understand each and every pixel. So you can see it's some rooftop of a building. So when I zoom into this, you can see the beauty of RGB colors. You can see how RGB values are incorporated into pixels, and those pixels come like an image. Yeah. So I'm zooming into it. Oh, yeah, cool. So each pixel got that three values you can see. Yeah. So each pixel have RGB value which defines. So all this together is combined and becomes an image, right? It's how beautiful it is, how a robot understands and looks at an image or a real world, uh, how it perceives things, right? So these are all numbers. Robot deals with all these numbers. It's just put it in a column and it's just maths and formulas that's done together. Yeah. So this is what we are going to deal with. So if RGB looks like this, then what about black and white? I guess I just discussed it earlier. See, so black and white image is only white and black. That is two values. But RGB is like red, green, blue. So all this together will have certain something mixed up, and that's how a certain color shows up. So that's why an RGB value is given. So imagine it like a grid. So it's like a one dimensional grid, and then you just make it 2D. You can put two colors, and then there is a 3D. So there are like RGB. So that's all together becomes a colorful image like this. So basically, grayscale is something that we deal that is called for black and white images, and RGB is the colored images. There are many other like HSV and CMY. It's all it's all different kinds of uh, types of coloring how we use it in an image. Yeah, just a second. I'm just bringing out the presentation back. Yeah. So we are back to the presentation. Yeah. Yeah. So we understood how light comes and becomes an image, and how all these columns or grids of numbers becomes a image. Huh? And then we understood what a grayscale and a color RGB color is. So as I mentioned, 8-bit pixel value is ranging from 0 to 256. Basically, it's 255. So that's the range. And then at the same time, an RGB color is a three-channel color. So it has three numbers, each having 0 to 255. Yeah. So pro photography people actually uses a 16-bit for each. That's a huge number, right? That's why all these images that you see have a certain uh, storage value. Yeah. So I just showed you how exactly each value looks inside an image. Yeah. So let's see. Let's move on to the next. So now that we understood all this RGB and grayscale value, while this works well for computers, it's not how human naturally think about colors. See, we don't describe as an object in front by its RGB values. Huh? We can't just look at a color here and say it's, R is like some 27, G is like 37, and B is like 255. Oh no, I don't know what that color is. Yeah. So we simply say it's red, right? If you look at a strawberry, we'll just say it's a red color, right? We can't say the value out loud, what exactly the value is. So we transform this RGB image into an HSV color model. So why do we call it HSV? Hmm? Okay, so HSV is more intuitive. Huh? So what happens in HSV is HSV looks more like how we define the color. So we'll look at something, we call it red, regardless of uh, day or night, we can just look at that and say it is a red color, right? That's how HSV is defined. That's how the HSV model works. So, to understand how this RGB and HSV is visualized throughout the whole process, you can look at this. So, RGB is basically having a cube. Huh? So, every pixel has three values, that is R, G, and B. So you have to define certain for R and certain for B and certain number for G to get a certain color. So imagine I want to get a color of yellow over here. I have to define all three columns and get that number. Yeah. At the same time, for HSV, if you look at the visualization of this HSV, how you can actually understand this like a cone. So you can see it's like an angle. So in a circle, this section is red. And if you go away from the center, it's from white to a brighter or vivid color of red, right? Now, as you go down, the saturation or the value, what happens is it becomes dark. So white is here, it gets black over here. So basically, the red gets darker in every section. It's beautiful how we look at it and how we describe the color sense in our own way, how we understand. So this separation makes many image processing tasks like color detection and segmentation much more easier. Here, let me explain you what exactly HSV stands for: hue, saturation, and value. So what I told about the red color is basically the hue. Hue tells us what the color is. Saturation tells us how pure or vivid the color is. So saturation spans across this, and hue is like a circle. You go around. So if you want to change the value of hue, you want something like blue. You will go at an angle, and you will get blue here. And if you want to change the saturation, you'll just go more. You'll go in a y-axis, huh? And a y or x. Basically, if I take it as a x and y, okay, I'll tell it as x-axis. And if you want to change the value basically gives you more brighter side of the blue. Yeah. So this is how we understand. Now let's see how exactly this RGB and HSV makes sense. So the transition is basically more powerful as it shows the color image processing is just choosing which spreadsheet to be performed on. It's like you have R, G, and B, and you have HSB. To get a certain color, you need to select certain R, G, and B value. But for HSB, you just select one color, go through S and B. So I'll show you a demonstration how exactly you can use this and make an understanding out of it. Yeah. Wheel in front of you. The wheel is lying on the table, right? So let's see how RGB and HSB value will make a huge change. Yeah, so I'll run a small script, and this script will basically. So this is the raw image that you are seeing in the screen. So I'll be running a small script, and you will be seeing the output.
So Ajay will be taking care of if anything message Ajay. He's sitting in my position. He has access to it.
Okay. Yeah. So this is the raw image, and I'll show you how I took out the detection out of it. This is basic. So what I'm doing here is a small concept called masking. Yeah. So what happens here is I take one image and just select the color. I'm selecting a red color. I'm telling red color, and I spread a sheet across it and tell I only want to see the red color on the whole image. And that's how I create a mask. And then what I do is I lay it over it and then only show what exactly the difference is. So it's like subtracting and a certain color from the whole image and showing what exactly the difference is. So this is what I did. So that it's more visible to you, how the color can basically impact. So right now the whole scenario is brightly lit, huh? And I've selected a RGB value for which I've created a mask. And this is what is visible. A robot can see using a RGB color like this. Now, what if I change the scenario to a darker environment? Let's see what happens with the RGB. So I'm going to create a more darker environment. Yeah, now you can see again. So I'll show you the real image. See, previously I showed you a really, so what you can see here is the raw image from the camera. I made the scenario more darker. Now what happened is when I use the same RGB value over that mask, the whole detection or the selection is gone. Oh, okay. So what do you think about it? Okay, I'll tell you. So basically, the robot doesn't know when it gets dark, it's a red color. It thinks I had a red color that you defined earlier, but that doesn't look like the same red color that you defined me. You told me earlier. So that's the problem of RGB. Now, let's try out HSV and see the beauty of it. So I'll bring back the same scenario of the brightly lit condition. Yeah. So you can see here, this is a brightly lit condition, right? Like earlier, as I mentioned. So if I bring back the mask, still. So just like RGB in brightly lit, HSV also detected it properly. And it's pretty clear. The edges are clear, the small details that you can see. You can basically map it and check. Sorry for the uh, it's not fitting in the screen, but yeah, I hope you can just figure out. Every detail is clear on this. Huh? Yeah. Now I'll show you the beauty of HSV. Let's see. So I'll make the scenario more darker. So all this is happening in a real scenario. I'm trying to bring back the lighting condition down. Let's see. Give me a second. Hello. I hope I'm audible.
Yes, you're audible.
Cool. So the human perception is so beautiful, right? So you can see that the 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 condition field when I use an RGB value in a bright condition, no, sorry, in a darker condition. But the HSV value actually succeeded when I used from a bright condition to the dark condition. So HSV is how we actually perceive the color. You just look at something and tell it is a color, it's a certain color just by even if it is dark or bright. So we tell the robot you use a HSV value and understand that that color is red even if it is bright or dark. So so that's the thing. In RGB, to make an image brighter, you need to add a number to all the RGB values, R, G, and B. That's quite tough, right? So yeah, so let's see next. Yeah. So this R, G, and B values, it's actually hectic to define all these values just to define a certain range. So if you want to define a range from this point to this point, you need to figure out all the R, G, and it will fail. It will only succeed for that certain condition that you tuned it for. But for HSV, you define a sector of the whole cone, you can have the whole thing visible. So any detection, any color, regardless of the brightness or the darkness of the scenario, you will succeed. So that's the beauty of how human perception works. Yeah. So let's see the paradox of purposeful blurring. Now that you understood how an image is formed and how all these RGB and HSB value is used to detect a certain object or a colored um object in front of a camera, right? So now a robot can tell it has a certain color, it has a certain a detailed color in that object. Now we have a problem here. So what happens is during all this image acquisition, there are certain noises. These are all unwanted noises that shows up in the image. You take an image, you thought like it came out really well, but at the end when you go for processing all that or doing something or certain uh, application, you realize that this image is basically too much cluttered or it has so many dots and unwanted things in the image. You can see just like an example, this image, it's a portrait, it's a painted portrait. So so it's a created scenario basically, but you can see how this image is so noisy. You can see every kind of color dot on this image. I hope everyone, it's clear, right? It's quite washed off and it looks like so many dot. It's like it's messed up. You know what? All these photographers don't like all these white dots and stuff. They make sure they capture the quality properly.
They will make sure this doesn't happen, because they can't just publish this all these kind of things in a album, right? It will be too bad. But yeah, let's see. What if suppose this kind of scenario comes when you are doing some kind of perception, or a bot is actually moving, and you come out with a scenario where it is a dark and all these dots are coming up, but the object in front of you is something that you want to detect. Yeah. So this is basically called noise. So to a computer, this is basically a sudden change that look exactly like edges to it. So what happens is there are certain values that pops up like a impulse. Some values will be like too deep, so it's like dark and too dark or too bright. So that's why all these noises comes. So as a result, the algorithm may detect shadow boundaries instead of a real object. So it's basically a problem in the whole scenario, right? So one of these noises. So let's understand what are these exactly noises looks like. So there is something called salt and pepper noise, which looks like gray, white, and black colored dots popping up in the whole image. So these are basically the impulse noises that I mentioned. So impulse noises flips random cells to pure zero or directly to 255. And yeah, it's quite bad when you look at the image and it has all these noises. So robot finds landmarks by looking for sharp changes in their number. So so these becomes a fake corners everywhere, right? That's bad. Yeah. So because of these challenges, we often need image enhancement techniques such as filtering, blurring, and sharpening before performing tasks like edge detection or object recognition. So we remove this noise and we get a proper image so that we can work directly on those images. So what do we do? How do we remove all these noises? That's the thing. So you see, an image is like a column of all these numbers. What if we do some simple basic mathematics on this whole matrix, a big matrix using a smaller matrix? That is what is called convolution. So what we do is we blur certain sections or the whole image. We blur it out so that the the noise or every pixel that is popping up and down is averaged out and it's giving a certain value. It's like smoothened. So blur is something that solves the problem of noise. Yeah. So this kernel that you see, it's a small square that it's visible, right? Yeah. So it's a small square. You wipe it across the whole image. Like, so this small square will go from this point to this point to this point. It will do the full math. It will multiply across the whole image and make it even. That's how a convolution is done. And that's how a blur is implemented into a noisy image. It's beautiful. So I'll show you an example of a real world noisy image. Huh? So there are different kinds of noise basically. That is what I told you, the salt and pepper noise. There is Gaussian noise. So Gaussian noise is the most, uh, you know, most effective noise that you see in real life. So a camera, if you keep it in front, you will always see a Gaussian noise across it, unless you pre-process it. So all these cameras that we have in our phone, right? All they all have noises in there. It's all about pre-processing and then processing and showing it to our screen. That's why it looks so beautiful. But they do have noises. Yeah, let's see how all these noises looks like. Let's just create a scenario and see that. So I'll be flipping my camera again. Give me a second. Yeah. So now you can see this is an image, a raw image that is coming out of a camera, right? Now I'll show you. I'll be inducing noise into it. I have a small slider over here so that I can induce some noise. So I start inducing noise. You can see some noise popping up. Yeah, you can see all these dot small scenarios coming up. If I increase, let's see what happens when I increase. So I'm inducing a Gaussian noise into the whole scenario. See how bad it becomes. Now it's all washed out. I can see all kind of colors here and there, moving here and there, right? Okay. So let's see what exactly happens. I'll put a, a small amount of noise. Yeah. So these kind of noises are more realistic. I'll put more like this. These are the scenario where it is more realistic. What happens is a board is moving and you have a low lighting condition, and this kind of noise happens because the shutter basically that captures the image is actually really slow, so that all the bright light it needs should enter. So it captures all these noises during capturing all this image. So what I'll do is I'll induce small amount of blur. You'll see the magic. Okay, so just because I'm implementing a blur here, it won't show up in this image. So this is a raw image that I'm feeding into the robot. But the robot don't want to see this raw image. It needs a certain kind of other image that it wants to process in. So what I'll bring is, I'll bring in a masked image. This is where the robot is going to process all the information from. So I'll add a small amount of blur. See how beautifully all the noises are gone. Yeah, isn't it? Yeah, you can see here and there some noises. So, but that's not a problem. But our main goal is looking at the object over here. So inducing all this blur has removed all the noise. So I'm inducing a Gaussian blur basically. So what I'm implementing here is a Gaussian blur. So for a small amount of noise, to remove all that noise, I'm doing a small blur. Now I'll show you the raw mask that I implemented. So this is the raw mask. See how bad it is. If you try to detect some corner, it will show all these lines, these small lines that you see. It will detect all those lines and it won't show this is as a wheel. It will always fail for that. See, this is the raw mask that I mentioned. But after the blur, this is the case. It looks much more defined. It's more beautiful, isn't it? And this is the information that a bot will see after a pre-processing. It's so beautiful how at the end you give a bot what you want just by all this processing. Okay, I'll give you a small imagination problem to solve. Just imagine how your eyes solves all these small problems. Imagine how human eyes actually looks through all these noises in the air. How does it solve all that? Yeah. So what happens here is because all these challenges, we need these kind of enhancements to feed all this data to the robot directly. So this is basically called pre-processing. Yeah, so let's move on to the next. All right, I have another small demonstration for you to understand what exactly I mentioned about the kernels. So this is a website where you can actually explore how exactly the kernels work. So I told you I'm inducing a noise and then I'm solving it using a Gaussian blur. So this is an image. You can parallelly see the image is actually fully defined as a rows and columns of numbers. Now, you saw how I'm blurring the image and solving the problem, right? So this is uh, a really ununderstandable image, right? It's quite blurred or it's too much pixelated. So what I'll do is I'll bring in some sharpen. It's already sharpened. Now I can see a small amount of definition. This will help me define the structure, right? I can get some information out of it. Now what if I make it blurry? See, everything is blurred out. So one fact that we can understand from here is, so this is the small kernel that is going to sweep across all these pixels and come out with this result. The result over here. The right side is the result and left side is the image input. Yeah. So that's how these kernels work. They get multiplied by all the pixel values and then the resultant matrix gives us this image. That's how the kernel works. Now, if I put right well, it gives a different value. You can tweak with this and explore how a kernel works. Now, let's look at a more defined image. So, this is a small kernel. Now, I'm going to swipe this kernel across the whole image. That is how the processing is going on. Now, if I increase this value, you can see how the value increased here defines all the sectors of this image because it's getting multiplied. Now, if I decrease the value over here, see how it decreases the value. It brings more depth when I decrease the value. So here I can get more definition. Now it gets darker. So every value in this matrix actually affects the whole definition because it's getting multiplied. Basically, the whole the process of this multiplying across the whole image which basically is also a matrix is called convolution. Yeah, it's beautiful how this pre-processing is happening, and this all happens behind inside a processor. So now that you have understood how blur is done, so point here is while a human photographer hates all these blurry photos, an image processor uses blur as a vital tool by intentionally mixing each pixel with its neighbors. You see, all the neighbor pixels are made together. It's like if one is too high of a value and another one is too low of a value, it's all made together. So we replace every cell in our spreadsheet with the average of its surrounding. So why it works is noise is high frequency and object is a low frequency. So the filter's job is to average it out and bring it to a state where it is, both can cancel each other. Yeah. So just by squinting through the blur filter, the robot ignores the distracting grains of the salt and pepper or Gaussian noise, and finally sees the an object it is looking for. And we trade the fine details for robustness. So let's move on to the next. How after understanding a color and then removing the noise, how we can go forward with the perception, the geometry of perception. Yeah. So perception is something a body is doing. It's trying to understand what an object is in front of you. Now the thing is, it knows the color. It has also it got noise, and you just remove that noise, and still it ends up with a color, right? You saw the black and white defined circle, the wheel defined was coming out with, right? Yeah. So imagine a robot is tasked with picking up that wheel after pre-processing the whole robot's brain. It identifies it, right? However, simply knowing a shape exists is not enough for interaction. It needs to know where exactly it is. To accurately extend its gripper and seize that object, the robot needs to know exactly where that ball is in the whole image. So it always gets a frame. So in that frame, where exactly is that object? It needs to know. So this is where we move from low processing to a mid-level processing. That is basically extracting the things like attributes like the boundaries. So when we know a boundary, we know where exactly that wheel is in the whole frame. Yeah. So it's all maths. So what do? We do edge detection. See, there is a difference between the background and the object in front. Now we need to know where exactly is that image in the whole frame. That is when we do edge detection. So to solve this, there are many types of edge detections. So edge is simply a sharp jump in pixel value, and it basically defines a certain object from its background. So you can trace those jumps and get that object's outline. So you can see over here a solid blob. Basically, it's a red color blob and a white color background. Now you want to define the edge. Obviously, you can do it easily, right? Because there is a white and a red. You just see the change in the color, and that exactly you find the edge or the whole boundary of that object. So there are many kinds of edge detection. We'll be looking in how a canny edge detector works. It's quite widely used, and it's basically the tool used to detect small amounts of or basically many applications they use it. So outlining what object should grab. So an edge is like a discontinuity in pixel intensity. So a sharp jump between the numbers in our whole frame is basically what it detects. So algorithm basically works like this. It smoothens out, it finds the gradient. Gradient is basically the change from one pixel value to another pixel value. And then a thin line is drawn at that exact point where you can see the jump. And then you just link them up to a certain threshold, like, increasing the thickness of the line to show more pronounced edge or certain something like that. It depends on how you put it through. So Gaussian smoothing is something that we did previously. Now the gradient computation, it is a small math. It just looks for the change of pixel, and then eventually the magic happens. You see a whole full full edge coming up in the whole thing. So now there are other types of edge detection methods that is called Sobel or Laplacian or Krish, Compass, HED. These are all various other types. But now we'll be exploring canny edge detection. Yeah. So let me show you how we are doing that. Yeah. So you can see there is a somewhat I can see the edges of the circle, right? But here I can see the whole thing. And this is the image basically. Yeah. So what exactly is going on? Are you able to figure out? Okay, let's do one thing. Let's tune it a bit. So this is the output image basically. This is how at the end you will be able to detect an object. So this is what a robot will basically process and see. And this is something, this window is something what is happening behind the process. Getting it? So I'll bring in some controls to tune it. So what is happening here is I'm trying to detect only pronounced sound, pronounced lines rather than bringing all the small lines. So the low, if I increase the low, I'll see all the lines on the table. Just a second. Yeah. Yeah, low, if I decrease, I'll see all the lines on the table. And high basically brings only the lines that are completing the whole structure. Yeah. So I'm increasing a bit more high and increasing a bit of low because I don't want unnecessary structures to be formed. I'll decrease a bit of high. Yeah, it's almost forming the object. So you can see it's pronounced here. So yeah, so I'll show you the comparative difference. So if I increase high and low, what exactly happens? So what happens is in many scenario we fail to tune all these uh, small sections in image processing, and we often end up debugging the wrong things. That's why this kind of understanding is necessary. So if I decrease the low, you can see unnecessary object detection popping up in the whole. So if you see in the whole outline, there will be some random lines popping up. You can see there will be some green color lines popping up in the whole screen. Yeah, see the dots are popping up. Now if I increase high, yeah, basically it's a low noise area. That's why it's getting detected since the scenario is well lit. So yeah, so you can see the process exactly happens like this. Since that it makes up a proper circle, it will complete that whole circle properly here. That's why the outline is well pronounced. Yeah. Yeah. So basically, in image processing, we are moving from treating the image as a data, like we initially understood. It's a grid of numbers, right? It's like a spreadsheet of numbers to treating it as a information. Huh? By using these detectors, like we just completed the whole detection of edges, we transform a raw spreadsheet into a geometric map, so that a robot can actually navigate and grasp and understand its world. So we have defined a certain position, defined a certain region in the whole image, and it will go and capture it. We have defined the edges also. So the robot knows, that is the place where I have to go and capture it. Yeah. So now that we have defined the edges and all, how will we differentiate between if it is a random thing or if it is actually a wheel? Yeah. So that's basically called object recognition. So, like we saw, it's basically defining a certain circle or square near the wheel. So, if I bring in something else, so I'll show you what happens when I bring in something else. You can see here, I have brought, okay, I'll bring this one. So I've brought both of these. And I'll run the same canny edge detection on it. See, it detects every kind of object in and around. So because it's a change in the pixel value, it will detect all these things. Now what happens in the actual output? It also detects that. Now again, if I try to lower it, it will detect other stuffs. So the beauty here is now that it's able to detect all these edges and differences, and it is able to pronounce this is a wheel, but something else over there is also completing a certain edge or certain something over there. How will I tell this is the wheel or this is the wheel? That is the problem that is addressed in the PPT right now. Yeah. So the sketch full of anonymous blobs. Among these blobs, what exactly are you trying to detect? Is it or not? Yeah. So the problem is multiple objects is on the table, and how the robot knows which blob is the shape or the wheel. Huh? To solve this, we must move the mid-level processing, as I mentioned, to a object recognition level. So the bridge here is contour detection. What exactly happens here is before the robot can make a decision, it needs to group all these edge pixels into distinct entities. And that is basically called a contour. A contour is a boundary of a connected component. It sets off a foreground pixel. It's like it makes it stand out among the whole foreground. And basically using a transformation, you can just figure out, basically transformation is like a tools. Just imagine it's a function that basically tells if it is an object A or object B. So now instead of million random pixels, the robot sees if it is an object, it sees as a object A and object B. So the whole decision making is through shape and size filtering. So what happens is step one is group the whole pixel. So there are scattered edges over here. It's grouped together, and then a clean object A and B is coming out. So you must have seen there are two different edges were detected. So it's cluttered together, and it's called what kind of shape it is. That is how shape A and shape B is coming out. So these all can be done like shape and sizing can be figured out by using area, circularity or eccentricity. Basically, how area is, since the edges are covering a certain area, It's like completing a whole circle or a square. The robot counts the number of pixels inside each contour, and the ball, if it is much more smaller than uh, the wheel, or the ship is much more smaller than some other object, robot can immediately filter out anything too large or too small. So there is a difference right now. There is a difference that we can say from area. Or since wheel is a round shape, we can say any other object that is not round in shape can be omitted out. At the same time, the eccentricity. It's like how oval or how elongated the shape is. Yeah, that's how this object classification can be initiated in the early stage. Yeah, so if area is 500 to 700 pixel and circularity is more than 0.9, it's a ball. Otherwise, the regular shape is an apple. So here it's telling about the difference between a ball and an apple. Yeah, so I'll show you how exactly this is happening. Yeah. So you can see here, the wheel is perfectly given as a round shape, but it's also says some other object that is being detected is not round, so it's not a wheel. See how a small mathematics can actually define if it is a wheel or a object. Again, I have a small tuning. So if I increase the minimum area, that also will vanish. Roundedness. Okay. So when I decrease the roundedness, so the percentage decreases. So it says, okay, this is also a wheel. I'll increase it more, and it's about 70. So yeah, this is the wheel. So minimum area should be less or high. Yeah, basically when it is high, it will remove all the unnecessary detections at the corner and still consider this wheel over any other thing. Yeah. So that's how we do a contour detection or something. So if the object's area is between certain thing, or circularity is above certain level, then it is a wheel. If there is more irregularity, it's some other things. So here the robot isn't recognizing uh, uh, a view like a human does. It's simply maths. It's put all this maths in its way to a decision by comparing the number and all this, shapes and area to set the rules we gave it to. That's how it does all this recognition and comparisons. Yeah. So now we know we are able to differentiate between objects, and a bot that is actually moving in an area is basically trying to figure out that is an object over there. Now, how is it going to understand where exactly the bot is? That is also a beautiful image processing part. Yeah. So up to this point, we just used all these colors, edges, and contours to help a robot to recognize individual objects like a ship or a wheel, right? Even if bot recognizes every object in a room, it will still get lost. To navigate autonomously, a bot must perform self-localization, right? it should know where exactly it is so that it moves to a next position. So this is the process of determining its own coordinates within an environment. Now, what do you think will be so I'll give you an example. For a human being to walk to a certain area or go to a certain street, we know a street name. We'll follow that street name, or an arrow is given to go in that direction to go to a certain street, right? And we use house numbers and house names to understand a unfamiliar neighborhood, right? But bots use something else. For bot, it's something else. And that is basically called a fiducial marker. There are many kinds of fiducial marker. It can be like Aruku marker, April tags, and it's their version of street signs that they can figure out where exactly the bot is. So these markers are reference objects placed in the camera field of view. They consist of black and white square that you can see. Yeah. So it actually looks like a QR code or something. It's similar to a code. You can look upon it. You can understand what exactly. So because these patterns are similar to high contrast, it's like white and black. It's a pattern. It's the camera can identify, the bot can identify them faster in any environment, and more obviously, it can just recognize these things upon compared to any other natural objects. Yeah, so even if you keep it in a dark area or a bright light, it will still recognize it's a marker over there. So the only thing here it's giving here is an ID and a position. So there are many kinds of markers. This is one of it. So each marker has its own ID, and each marker gives a certain 3D position as well. So I'll show you how beautiful these markers are. Just a second, I'm just switching the camera. Yeah. So as I mentioned, each marker has its own IDs. So you can see there is ID 3, and then I'll bring, yeah, I brought all the markers. Don't worry about the image. It's because of the brightness. Yeah. So you can see there is ID 1 over here and 2 over here and 3 similarly over there and then 4 over there. So all these together gives the IDs, and so I wrote the script in such a way it finds the center of the page. Now, if I move this page anywhere else, it will basically give the center at that position. See how beautiful it is. Across the screen, it is giving me the center of the page using these markers. If I move anywhere else, yeah. Yeah, there is another beauty about these markers is that you place it in any position, it will give you the position of that that area in the frame. So I'll show you another demonstration. So you use these kind of markers for the boss to look at and compare its location. So if suppose you've placed 2-3 markers in a certain area, you can just actually look at that markers and then figure out where exactly you are standing compared to that marker. So that gives the position or the coordinate of the bot in that area. So I'll show you how it shows the 3D position. Yeah. See, So each marker has its own 3D position. Now, if I tilt it, you can see how the 3D axis actually tilts along with the whole thing. See, in 3D, you can see how it exactly is this position. If I just turn the whole thing, it can detect at a tilt also, at an angle. See that? How beautiful it is. Yeah. So the true magic of these markers is that they provide more than just a name. It's like it gives the position of the bot in certain region. You can just compare it and move around. Basically, these are actually used in real world applications of position of the arm in a whole scenario, so that it understands where exactly in 3D position the arms link and joints are going. So when a bot sees a marker, it exactly extracts two vital information, that is an ID and the position. Without needing a complex 3D sensor, the bot can determine if it is tilted and how many centimeters away from a goal it is, or what angle it needs to turn to align itself perfectly. So it can also be used for docking. So after a certain scenario, a bot wants to go and dock at a certain angle at a certain location, you can use these markers, and especially you will be using a camera as for perception. So that time, yeah, these markers are basically useful. So by reading these digital street lines signs, a robot transforms a raw spreadsheet of image or pixels into a precise coordinate system for navigation. Yeah, now that we have understood that this digital signs can do all this beautiful, uh, you know, uh, position and all, I'll show you a really beautiful example of how perceptive transform works. So in a perception, you look at something at a certain angle, it gives you a certain shape, right? But perspective transform is something more beautiful. I'll show you. So we are at almost at our last demonstration of this. Yeah, so as I mentioned, two gifts from the one glance that we get is ID and position. So let's see a small last example that I want to show you. Yeah, I hope it's visible to you all. So I'll do one thing. I'll increase the height a bit more so that you have much more area to cover up. Yeah, so now we have more area that you can see. So the field of view is more. Yeah, so what I'll do, I'll place a ship over here, a wheel over here, and another ship, a ship, a wheel, and a ship. Now I'll bring to you a more interesting view. Look at this. So this is a perspective transform of this image. Now what I'll do is I'll move this thing across the whole frame. Look at the perspective transformed image. See that? So now just imagine you are feeding this perspective transformed image to a bot. How beautiful it will. It will look at that small area regardless of anywhere in the whole frame. You can see it in real time how it actually moves, but it only detects at that certain area. Now, this can also be in a really extreme cases, like you keep the angle of the camera at really extreme uh, from sideways. That can also happen. So if I put this, if I just tilt it, you can see that still be the same shape. See? Yeah. So from all this, let's just summarize what we did from the whole thing. So from a grid of numbers to a bots that navigate. Just a second, I'll just come back again. Yeah. So when a bot starts to understand an image is basically all numbers, and that on that numbers we see all these colors, that is three colors RGB, and how we understood the difference between the RGB and HSV and which one to use. And from that we understood that there will be some scenarios where it can be noises, so we clean all those noises and get with the object. Now the processing part where the object is clean. Now we do some edge detection. From that edge detection, we can understand how this object is different from the other object. And from all this object detection and uh, contour detection, we come back to the same thing, that is fiducial markers. And this fiducial markers is basically detected using all these pre-processing techniques, which goes behind and at the end comes out with a small beautiful information that is poses and IDs. And that's how the whole beauty of perception of a bot can work. So this was a small example of how the whole perception pipeline works and how image processing is done. And every step solved the problem the last one created. And yeah, so enjoy. So now we are open to questions. If you got any questions, you can raise your hand and we can clear.
We are open to questions. If you guys have any doubt, you guys can put it over here.
Session. Thank you again for joining. We're looking all of you forward to participate in eYIC and eYRC. Thank you. Have a nice day.